Today's Bob Pease Show is brought to you by the properties of the Hearst Electronics Group, including Electronic Products Magazine, IC Master, and EEM, the #1 directory for electrical engineers looking for components and suppliers. The Hearst Electronics Group, delivering new and exciting products serving electrical engineers, including a new reference directory, daily product highlights on electronicproducts.com, and newly planned upgrades to IC Master. The best place for you to start is electronicproducts.com.
Almost live from National Semiconductor, the analog IC design and manufacturing capital of the world, it's the Bob Pease Show. Here's your host, Bob Pease.
Hi, this is Bob Pease, and we're going to have a very nice session today about current sources and stuff, analog stuff. So we hope you can join us.
Where did the ladder come from, Bob?
I don't know. The ladder's been here for a long time.
Oh, we got the ladder out of here. All right.
That's okay. No,
So we're going to talk about what current sources?
current sources. And the current sources we're going to talk about are what's all this signal current source stuff. And now, put down your damn magazine, will you?
Why, it's electronic
I don't
products.
care.
I love this
Electronic
magazine.
Products. It's a good magazine.
Lots of
okay.
good stuff.
We got Paul Rako.
How you do, Bob?
You gonna meet me at the baggage claim in Boston?
Yeah, we're going to Boston
Yeah.
tomorrow, huh?
Paul
Oh, boy.
Grohe
Hi.
and Alan Martin. And we're all going to talk about a lot of current stuff today.
Well, where's Alan from? He's new on the show.
He's from National Semiconductor.
One of our guys, huh?
He's one of our guys.
He's a FAE, right?
Yes.
correct.
Thank you.
Do we give you a car, let you drive around and
Yes,
stuff?
they do.
Oh, good. Well, if you're in
Okay.
the Bay Area, look for Alan. He'll be coming around calling on you. Mm-hmm. So what do we got today, Bob?
Oh, we're going to be talking about analog current source stuff, signals and current sources.
If you were the czar of band gaps, are
Oh.
you like the prince of current sources?
I'm the prince of current sources. And this is the current source I discovered for the session in the fall of last year, 2003. And I'm going to explain a little bit about this because I explained this to about 30,000 people across the globe. But I won't spend much time on this. I won't waste your time much. So we're going to be talking about all these current sources, such as you have a voltage reference and a current pump that looks at the voltage reference and it works. Now, how do we do this? Well, this is called all this signal current source stuff anyhow. We're going to look back at the year 2003, excellent high precision 1 amp current source.
Let's reuse that heated Zener, right?
We do use, this
LM
LM399 has a heater and a Zener, which holds it at 85 degrees C, a very good Zener reference. We put it through a resistor divider, we feed it to an op amp, which then forces out a current. So we got 2 volts here, 2 ohms here, 1 ampere here, coming down through the whole thing into a load. What do you want to have for a load? Plus minus 2 volts, plus minus 5 volts. Fine. The output stability is the order of 5 parts per million. So for full details, we're going to have this stuff eventually on the web. You know that? We got to have all this stuff on the web.
Now, parts per million over temperature or time?
No,
how's that
5
mean?
parts per million per a couple of degrees C. This resistor was not perfect.
And that's where the TC came in.
Most of the temp code comes from the resistor because we can't make perfect resistor. We can't buy perfect resistors unless we want to pay $1,000. You know, for $1,000, we could get this resistor at 1 part per million per degree C. But I'm not going to do it.
No. How about this Charlington? What did you call it?
Charlington.
Charlington,
It's
because
a
it's
triple. Darlington is 3. Any ordinary junk transistor that can put out an ampere will work fine. Here, you need some resistor here to help turn it off. You need some base resistor here to keep it from oscillating. 50 ohms, nobody cares.
And 3 transistors was cool because a FET would have a big gate capacitance that might cause some oscillations and some other problems.
So a beta of 3 million gets you pretty
That'll
close.
get the job done.
Now, why do people like voltage sources and voltage signals? Obviously, I'm pulling these pictures out of the left-hand envelope. Well, why do people like voltage signals? Because everybody can see the signal. Oh, you can look with a scope or a DVM or a buffer. You can do all these things. Now, why do people not like current signals? Every current signal is a receiving antenna, and it can pick up horrible noise from nearby noise sources. You have a current signal going to somewhere you want to look at a signal to the ground. Noise, noise, noise.
This is what they call a photodiode amplifier, a high impedance amplifier.
Well, it's a high impedance.
It's a current source.
It's a high impedance noise detector. And you have to shield the hell out of it, and it's very important. But this can be partly alleviated by using shielded cable. You got a photodiode here, what's in current. The cable is wonderful because it cuts out the noise, but it adds capacitance. And capacitance is usually, at any bandwidth at all, your enemy.
It's either going to kill the bandwidth or make instability or all that bad stuff happen.
Yes, either one or the other or both. And the cable ain't even cheap.
Yeah.
It'll hurt your ability to see the signal. What else do we have? Also because not everybody can look at the same signal. If I shove a current into here, you can't look at it. It's a pain. So, on the other hand, why do people like and use signals? Some applications really do like and need current drives, such as LEDs like a current drive, white LEDs, flashlights, fast LEDs, lasers like current drive.
The telephone company, right? That was smart, making a current loop.
Yeah. But there's voltage and current. It's fairly high impedance. Now, the problem is you can't drive voltage into an LED. Now, LEDs and lasers really like and need current drive. Here's a current source. You take an old LM317. It's a wonderful old circuit. You probably have some lying around. You put some ohms across it. You could have, with 120 ohms, you'd have 10 milliamperes. You had 12 ohms, you'd have 100 milliamperes flowing down through here and here.
There's a reference voltage, right? 1.2?
It's 1.2 volts, yeah.
And so this adjust terminal is always 1.2 volts below this guy.
Yes, exactly. Good
so
point.
by putting that big resistor there, it forces a
that could be
constant voltage across the constant resistor.
But that could be 1.2 ohms. It could be 1 ampere flowing through either this load or that load, either or both.
If you put a big old 220 package, right?
But it ain't very efficient because you're going to waste 4 volts in this area. So it's a wonderful current source in concept. Here's another pretty good current source, and I don't know where this quits in concept. If you put 6.8 ohms, you can have 10 milliamperes. If you put 0.68 ohms, you could have 100 milliamperes. You could have an ampere here because the LM334 has a 68 millivolt sense voltage, which is sort of proportional to absolute temperature. And it turns on this stage, which could be it could be a Darlington, which drives a heavy load. Now, what is the voltage across the load? You got 4.5 volts here, you got ground here. You could have 4.4 volts here and 0.1. You could have 4.3 volts here. You could have an extremely high efficiency regulator.
And then this, like, you can always source connect the FET, right, and get kind of a current source, but the TC's all over. The LM334 gets
the 334 could drive a FET, so you'd wind up with 4.49 volts here, 0.068 volts here. You could do a lot of fun things. So if you're going to ride a flashlight, if it's 4 volts or 9 volts, you don't care because anywhere in between, the load will get full current.
And the 334 takes care of a lot of the temperature
drift. The 334 can servo. It's got a lot of gain. If you put a FET here, you might have to put a resistor here. It might have to be a P-channel FET. So here's another way to make a current source that's not only efficient, but effective, and your LEDs love it.
We like happy LEDs.
Here's another current source. Oh my gosh.
Oh, that's a beauty. I worked on this
This
part.
is an LMH6533. It's got 4 channels of driver to drive outputs.
And 2 big output sections. This is to drive
To
DVDs.
drive fast DVD drivers.
One for the CD laser, one for the CD recordable laser.
And it's a new, oh, you gotta slide this up so you can see it. And it has all these channels of input and the channels of output current, and it can put out, what is it, 600 milliamperes? Well, it says 500 milliamperes or greater.
Right.
Now,
it really pushes a ton of
We
current.
had a technical problem one time. We were running this thing at about a lot of volts and a lot of amps, and we said, this is getting very hot. And the engineer said, oh yeah, it must be running at 150 degrees C. We said, I think it's hotter than that. We think it's 260. Oh, it couldn't be 260
Oh, that's the one we
degrees.
set up over the
Yeah.
weekend, right?
Yeah, and we ran it all weekend, and it ran all weekend at 260 degrees C. And over the weekend, we figured out how to measure the temperature of the die. We went in there and we said, if it was 260 degrees C, it would be blazing white red hot. And it was.
This is using the ESD diode, flipping around an ESD
Testing
diode.
the ESD
and
diode.
characterizing
and the
that.
thing
That
was
worked
so
great.
hot,
And no
it
one
was still
believed it.
working, and it
worked
lasted the whole weekend.
Actually, we left it on all week.
And then I had to pull the power off and go back and measuring things. We couldn't leave it there. But you turn on a current, and it goes on, and then you have AC on and off and on and off, and you turn it off, which is good for writing or reading bits on a CD. So this was very fast and very good. If you want to look it up at LMH6533. Thank you, Paul. Then there's a laser diode driver that's really good.
Fast, low noise.
And fast.
Yeah.
We got a block diagram that says, look at all these features. Now,
It's
we're going
all
to
on the
ignore
web.
that.
You can
It's all
get-
on the web.
Good stuff. Not just because I
Now-
worked on it. It's good stuff.
How do you use a remote sensor? No, this is the wrong. Oh, A is if you want to drive a diode, you need a current source. Fine. But B, what if you want to have a remote sensor? You have two long wires. You drive the current into a voltage. And the voltage is your signal. That's wonderful, except for one little detail. If you're driving long wires, long wires, the signal is pure over here. And by the time the signal gets over here, it's corrupted by Ohm's law.
8 ohms.
So, well, 100 yards of wire, it could be 8 ohms. You got to use cheap wire, you got to use long wires. So, people driving remote sensors are not happy with the resistive path to the sensor. Could this be fixed by heavy gauge copper wire? Well, you could help it, but you don't fix it.
Yeah. Some factories are going a kilometer with these type of current sensors.
Kilometer, that's almost 3,000 feet.
Yeah.
Could it be fixed by using 4 wires? Yeah, but nobody wants to use a 4-wire signal path. So, this is out of sequence. So, this is a place where current mode signals are useful to bring back a precision signal from 10 feet, 100 feet, 1,000 feet, 3,000 feet. Why? Because the wire's series losses do not grade the signal. 1 ohms, 2 ohms, 3 ohms, we don't care. 4 ohms, 5 ohms. The current through the ohms of the series path do not affect the accuracy. And the wire's shunt losses do not degrade the signal either. Insulation is damn good. The series resistance is finite. We don't care. So when the signal gets back, it's a current. You shove a current into a resistor and people can get full accuracy. So industrial guys and process control guys like current mode signals. 4 to 20 milliamperes, 1 to 5 milliamperes, 10 to 50 milliamperes. And they've been doing it for a long time. And we can't teach them they're wrong. We say, oh, you guys know what you're doing. They do know what they're doing. And we can help them by making it easy to read those signals. And it's not really true that only one circuit can see the current signal, because you put the current signal through 1, 2, 3 100 ohm loads. So is this 400 millivolts? Yeah, this is what's this? 400 millivolts. What's that? 400 millivolts. The current going through there is 4 milliamperes, or whatever the current is, big or small. The current source guy puts out a current that goes through all 3 places. You can read it and read it and read it, or read it again 4 times.
That's kind of convenient, like a party line.
It is. It's not perfect. So why do you guys need a current source? You guys are not bringing back signals from 100 yards of wire? No, you aren't. Or you may not be. But current mode signals and current techniques are often useful. Now, this is an inverted version of the big thing I showed you a while ago. I said, ooh, there's a current source. Well, this is a current sink. You set up a bias. You set up an op amp. Oops, let me move this down so you can see that a V supply is powering the op amp. And you put in a Darlington, you put out a precision current. Wonderful. But the V supply, you have to provide it. People don't like that. That needs a separate power supply. The major advantage of a 4 to 20 milliampere loop is it's self-powered. You don't have to provide power.
You send 2 wires out to the center.
2 wires goes out, no batteries, no nothing. Now, how can you do this? Oh, a minute. Did I do this right?
Well, with an X-Acto knife,
wait.
those 2 big cuts.
Yeah, I know. I
made
meant it. The formula is even out of sequence.
Okay, well,
we'll get to that in 12 seconds.
All right.
So here's a self-powered item. You provide power. The op amp runs off the power. It's got a sensor. It's got a signal, but it's got a reference. All powered by the I out. What's the output voltage? 4 volts, 8 volts, 10 volts, 20 volts, 30 volts, 40 volts. Nobody cares.
It's the current that sends the information.
The current does, but how about this voltage? This could be very high. Wait a minute. What if this thing has a lousy beta? A beta of 50, 40, 30, 20.
It's got a lot of base current, right?
The base current could cause a terrible error.
We hate base current.
No, we don't. Base current lets it work. The base current could cause current to flow. We don't care. Do I have this here? Yeah, that's the next foil. So here we have a reference voltage of 0.2 volts. This is minus 400 millivolts. The op amp says this is plus, this is minus. It makes current flow around this path. How the hell does it do that? It knows how to do it. Why does it know how to do it? We'll explain that in 1 minute. But what kind of op amp can you do this with? Well, the LM10 is a really good part, and Weidler invented that about, oh my God.
78 or 79,
78.
somebody said. They saw documents.
77.
That old, huh?
27 years ago.
Works on 1.2 volts, works on 40 volts, has a reference in it.
Yeah, it has a reference of 200 millivolts, but it doesn't really run on 1.2 volts in a circuit. Like it can run on 2 volts because you got to have a couple of volts. But it runs on a small amount of volts. It's got a floating ground. We snipped out this stuff. Here's a minus rail, which is, let me draw this. Here's I and I. Now, how does it work? What's the beta? It could be 40, 50, 30. Who cares? Because the op amp says, I don't care what this beta is. This current is going to be right. When this current is right, and this voltage is right, we don't care what the beta is. It compensates.
Whatever beta current has to be sourced from here anyway through the op amp.
If the beta is lousy, you turn on more current.
Yeah, it's got to return the same current, right?
Yep. The op amp forces the current to all be right. But how about the op amp quiescent current? It could be a half milliamp. It could be 1 milliampere. That's lousy. It'll ruin your accuracy.
That's an
but
error
it won't, because that error term is caused to flow through the whole loop.
Through the same loop.
And the op amp says, I don't care what this current is, or what this current is, or what all these currents are. It's all canceled out. So it's a good way to use that LM10 with full accuracy. So what about beta? We don't care. What about the quiescent current? The op amp's quiescent current. What about this current? We don't care. What if this is a milliampere? We don't care. It causes 0 inaccuracy.
Because it all has to go through this.
It has to go through that resistor. When the op amp says, this voltage is right, this is right, this is right, this is right, we don't care what this is, and we don't care what this is. And Weidler effectively had a brilliant idea on how to do this. Now here's another way to do it. You take an op amp with a voltage current pump. But what about the base current? Well, the base current is lousy. It might be 1%, 0.5%, 2%, the base current could cause a significant error, but you guys are free to heckle me too. So we put in a Darlington. It gets much better. Put in a Charlington, just like I did. It gets much better. But what if we sense the base current? Well, you got a beta of 77, you got a milliampere here, you got 13 microampere, you got a mess. But if we sense the base current and subtract it, could we do that? Yes, we could. Here's a solution. 1K, 9K, 10K. This is 10K, this is 10K. 1 meg, 1 meg, 1K. Let's say this transistor has infinite beta. Well then, at 10K, 10K, 1 meg, 1 meg, it works. What if the beta falls to 100? We got a milliampere, 10 milliamperes, 100 milliamperes. Let's say we have 100 we could have a milliampere here. We could have 1 volt here. The 1 volt tells us we have an error. 1 meg 9K, 1 meg 10K cancels out the error. It works down to 0.3 volts, maybe lower. So the ratio is 1 meg 10K, 1 meg 10K, 1K 10 ohms. The ratio is 100. And Carl Nelson, I got to admit, was the guy who invented this, but nobody remembers this. This will now work down to 0.3 volts. So here's a circuit where stupid design and brilliant design sort of cancel out. Yeah. So
Now
this
the op amp won't work at 0.3, right?
well, we would need a volt in the op amp.
0.9,
But this circuit, if you
there's
need a
some low
current
voltage
source
op amps.
at 0.3 and this was a volt, it would work.
Great.
So here is a elegant solution. What else do we have? Weidler wrote, he didn't just design the LM10, he wrote an app note, AN210, on how to apply the revolutionary new LM10. There's a whole bunch of stuff in there. Weidler, Yamataki, and they tested all these circuits. You got not only an op amp, but you got a ref amp that works at 200 millivolts. So you can make a 200 millivolt reference. You can make a 400, 600, 700, 800, 902 millivolt reference, which is very useful. Now here's the first thing he wrote, a shunt voltage regulator. You put this thing out here, which is proportional to the signal. You got a perfect voltage that's 1718 millivolts. But when you get a long wire way out here, you won't see 1718. So this is why current mode is brilliant, and shunt mode is not all that perfect for some applications. So here's an application that was written up in the LM10 data sheet of, it's good for some things, but it's lousy for others.
Just like all analog, right?
Just like all analog.
You got to think.
Things that are good for certain things are not good for other things. Now, here's a 2-wire transmitter for resistance sensors. Oh, this is found in that AN211. I'll scribble that in, AN211. You buy an LM10, you look at AN211, and you can do this anytime you want to. You get long wires, and the output is proportional to the signal.
Yep.
Good
stuff. They're on DigiKey, I checked.
Figure 14, yeah.
Get them overnight.
Oh, here's a similar one. Here's an LN35 temp sensor, LN317 regulator. This is out of sequence, but I don't care.
Yeah, this isn't from the LM10.
This is not from LM10.
This is a different
but
mode.
you trim this, and you can have a perfect sensor from 0 degrees C to 100 degrees C.
That uses the 30. You designed the 35, didn't you?
No, I designed the LN34, but I helped on the 35.
And the difference is, well, one's Fahrenheit?
One's Fahrenheit, the other one's centigrade.
Okay.
Remember I mentioned Carl Nelson? Carl Nelson designed the 35 when he was here at National.
Good man.
Very fine circuit. And the patent's probably expired, but we don't care.
That helped you become czar of band gaps, no doubt.
And we put this diode in series to protect it from stupid miswiring. You reverse the power supply, no harm. Does it waste a half a volt? Yeah, but this is working at 5 volts or something. It doesn't work at 1 volt or 2 volts, but the diode is a really good idea to protect us all from damage when some absent-minded person says, Same thing, same thing, same thing. This is calibrated 0 to 100 degrees C.
Wow.
Here's a single thing. Current transmitted for a thermocouple, including cold junction compensation. You put a thermocouple into an op-amp and it says, well, I can tell you the difference between the hot junction and the cold junctions, but I can't tell you what the cold... Well, this provides cold junction compensation with the LM334, which is a temp sensor. It's got cold junction offset and level shift.
So this measures the temperature where the wires connect, where it
Exactly.
changes from chromel aluminum.
Yeah.
How do you say it, Paul?
Chromel alumel.
Alumel.
Yeah.
Chromel
So that
alumel.
these wires have to be sort of linked
Isothermal.
to the LM134.
But that's all in the same area.
Just put it in the same
and this
card.
could be, because this is...
This could be remote by 10 feet, 100 feet. So this is one way of using a current mode. It says, now this doesn't say 4 to 20. It says 1 to 5 milliamperes. Why? Because some people don't want to waste a lot of current. So the same principles that give you 4 to 20 milliamperes can be used for 1 to 5. Now coming up, I think we got, still 4.
200 degrees.
I forget what it is. Oh, this is 200 to 700 degrees. This is voltage mode. So this is the kind of mode, if you've got a lot of wire, it won't work so well. So this is an imperfect version.
And that does use an LM10 again.
It uses the LM10.
Good old
Now,
LM10.
here's a version. Log converter. What's the light coming in? It's in here. What's the reference current? It's in here. How does the LM10 do it? The same old magic. The LM10 says every time you change the temperature by a significant number, this IR drop changes, this voltage changes, the current changes, you get 4. Oh, it doesn't say. It says 1 to 5 milliamperes. So this circuit can run on less than 1 milliampere. Here's the problem. You're running 4 to 20, you got 3 milliamperes to waste. On 1 to 5 milliamperes, you don't have milliamperes to waste. You have, well, 100 microamperes here and 100 microamperes there to waste.
Now, could you use that 394 matched pair you like so much there?
I
or is
love
that
the
overkill?
394. This is PMP. You know, if you want me to redesign this for the LM394, I'd love to, but give me an hour, okay?
Okay.
I can't do that today.
We'll come back.
Come back in an
All
hour.
right.
Now, here's an application where it's 10 to 50 milliamperes. That's another standard industrial application. You take this output current, you shove it through your load resistor. It's the same as 4 to 20. Now, the bad news is we don't make LM121A anymore. But we can replace this one with the LM394. I'll fix this one too, okay?
All
I'll
right.
fix it.
We'll do it in Boston, on the airplane.
On the airplane? Oh, man. We'll discuss that later.
Yeah, we'll need an extra tray table.
Well, we need
Drinks for
true
one,
tape.
circuits for the
Anyhow,
other.
most of these current sources are one directional. They're unipolar. They can source current, they can sink current, they can't do both unless you get out your Howland current pump. Move, move, move. R1, R2, R1, R2, you may have to trim it because 1% resistors are not good enough to get a high output impedance.
And so a voltage here sets a current there. Is
The
that-
voltage here sets, and this goes down and up, or this goes up and down. And the current is absolutely, and if these both go up and down, nothing happens. So it's a nice current pump. It is, what's the words, high impedance output, and it's differential input, and it rejects. You need a decent op amp.
We make
Or-
lots of those.
Yeah, we do. Or you can trim R1 a little bit. And you
What dominates for error, the TC of the resistors or the op amp?
In different applications, that is a good question. If you have this output swinging up and down, the match of the resistors may dominate, or the offset may dominate, or the CMRR may dominate. We don't know. You have to engineer this. This is not a simple circuit, and nobody has no good answers.
For the resistors, you could go to Vishay and get a network on a ceramic maybe, and
You
tra-
could.
and
You
they'll
could
track,
buy
they'll
10
track at least, right?
10K, 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 10K. You get some good Beckman or similar resistors, and that'd be good. You might still have to trim them because the op amp might be better than the resistors.
We make good
What's the CMRR of 100,000? That's easy to get. What's a matching of these resistors of 100,000?
Ah,
That's hard,
that's hard
to,
to
get.
get. .02 is hard to get.
.02 is
hard
hard
you can
to
buy
get.
a .02.
Yeah. So you
beyond
may have
that,
to trim
you're-
it anyhow.
Yeah, that's a good way to think of it. I like that.
You could put the trim resistor here at the output. Trim resistor, pot, wiper.
What do we figure, Paul? The other 60 dB CMRR is a millionth of a volt per volt, common mode.
No, 60 dB is a millivolt per volt.
Millivolt?
Yeah, millivolt. 60 dB, 1 millivolt per. In a circuit like this, it's hard to compute. If you want to compute what this circuit is doing, you have to sit down and do some maps of voltage and current. And it ain't easy. But if this op amp is only 60 millivolts, the output is not very good. 80 dB, 100 dB, 129 dB. The resistors will get you when you get to 100
Right.
dB. The resistors need to be trimmed. But if you have a good op amp and you trim the resistors and the op amp error, it's not bad.
And that's the CMRRs when you pull these pins up
Yeah.
towards each rail.
Towards up
If
each
it's 60,
rail.
and most op
Yeah.
amps get better than 60 dB, although it gets worse over frequency. Right, if you have a high frequency signal.
Oh,
that's
I should
another-
mention,
that's
this is
another
not a
headache.
fast circuit. Is it fast at a megahertz? Yeah. Is it fast at a kilohertz? It's okay. This is one slide I already wrote up. The Howland current pump can push output current in either direction, all four quadrants. Plus current into a minus load, minus current to a plus load. All these quadrants with plus gain or minus gain, but you need to have the trim. And it's not binary fast. Now, here's the move. Thank you. The improved Howland. Here we have R1, R2, R1, R3 plus R4 equals R2. Oh yeah, I forgot to mention in here. R3 plus R4 equals R2 for good CMR.
That's some real analog PowerPoint there.
You have to trim it. We trim the circuit as we go along. Now, if this goes up and down, no output. If this goes up and down 5 volts and the output is sitting there at ground or at 5 volts or 10 volts or minus 5 volts, there's no output current. The output current rejects things like V in common mode. It rejects op amp common mode. You do have to trim it, typically. It has better gain, it has better efficiency. This is a need for some real serious engineering to figure out what you're doing. It has higher gain because if you have a gain of 10 here, and then you have 1 ohm, oh man, you have 10 mhos. You can shove amperes into the load. So the gain is up, the efficiency is up. The efficiency of the basic Howland is lousy. But this can be pretty good. You have to engineer it.
And that's where AC gets in trouble, right? There's little stray capacitances all over, and try to keep the impedances
I don't
matched
even want to
is
talk
a lot,
about
yeah, is a lot
capacitance
tougher.
is really complicated. That's a hard circuit to analyze. Nobody analyzes it, and I only do it once a year. Now, you got a current source. It's a 4 to 20 milliampere current source. It broke. It's not even 4 milliamperes or 3 or 2 or 1. It's less than a milliampere. Something's busted. Something's wrong. How do you detect it? Well, we got AN300. And when we first published this circuit in Instruments and Control Systems, they said this was the most popular, voted for circuit they ever had in many years. You have a current. It's either 4 milliamperes or 20 milliamperes or somewhere in the middle. What if it's 3 milliamperes? The LM10 says, there's a problem. This IR drop is wrong. This IR drop is wrong. I'm going to change the current through the optocoupler, which then says it's busted. So here's a current loop fault detector, and it's in AN300. And if you ever need one, it's very valuable. What else do we have? We got a similar version with, 0.85 milliamperes detector for 1 to 5 milliamperes, or if you have 8.5 milliamperes detector, it's a good idea to add a transistor here because to pull down 50 milliamperes, you don't want ask the LM10 to do it. You want some help from a transistor. So if you ever need to know, is my 4 to 20 milliampere circuit working, a circuit like this may be useful.
Mm-hmm. Some of our LMV parts have pretty high output currents, right? 100 milliamps.
We
Is there
do.
something you can think of?
But usually, for
711
a crude application, the transistor might be fine, but we invite your comments because we're not saying there's only one way to do things. In the analog business, there's more than 5 ways of doing almost everything. Could we change all those circuits to 5 different ways? Probably.
On the way back from Boston, we'll do that.
Oh, man. We'll discuss that.
Wow, look at that.
We got a picture.
This is
No.
I'll show the side picture. It'll fit
I'm going to
better.
show the broad range picture.
This is Alan's backyard.
This is Alan's backyard, and he has a few meters. And he has a few scopes. And we will expand the picture to show Alan Martin is a true nut about high precision instrumentation. Oh, let me slide this up. I'm going to have to cut off your head.
That's quite all right.
It is? And
don't do it
here's one of
every
these
day.
meters to sense many amperes.
Yes, that's the HP 428B. It's a very fine instrument. It's unfortunately vacuum tube based, and they're not very reliable. So it's important to own more than one.
You need 2 of them to get it working.
Yeah.
Wait a minute.
What kind of toys you got
Now,
here for us,
he
Bob?
can use these 428Bs to detect, what was it, 20 amperes?
They're good to 10 amps full
10
scale.
amperes. Now, this is the 20 ampere version. Here's a little current probe shunt. Now, I brought this
Can we put it on top of Alan? Let's
Yeah.
put Alan
Well,
back.
yeah, yeah.
Move me out of the way.
Yeah.
Okay.
I bought
got
this
all
from
this stuff.
Fair Radio. And Fair Radio sells good junk, and if you don't need a 10 ampere shunt, but you need a 1,000 ampere shunt,
There you go.
there's a 1,000 ampere
So
shunt.
where's Fair Radio?
Oh, they're on the web.
They're on the web, huh?
They're in Ohio. They're good people.
Oh,
they have
anything. I was
honest,
born in Ohio.
good
So was
stuff.
Paul.
So here's a beautiful, and I have not run the amperes through it yet myself, but I will.
Oh, we'll do that. Lead acid batteries.
Yes, sir.
Okay, and I see the rating is printed on here that it's
Yes.
12 volts full scale at 1,000 amps.
It's not good for 120 volts. Not that it wouldn't survive, but it's not a great idea.
Well, is that the shunt rating, or is it
Well, that's the
millivolts?
shunt
The
voltage.
circuit rating.
Yeah, you could put that in series with a 1,000 amp 120 volt circuit. I don't know who would have that.
That's not a good idea. I think this is rated for 12.
That's a voltage rating.
Yeah.
It's the voltage.
That's-
It's a circuit voltage rating, and I wouldn't want to get pushy about it.
Okay.
So you put one of these in series with one of these, and we can say, "Oh, let's calibrate these guys."
Alan brought all kinds of cool stuff to show us about
Yeah.
measuring
Now,
current.
Yeah.
Alan, show me that machine.
Okay, earlier today you threw the gauntlet down and
Yeah.
asked me if I could measure 1,000 amps. And I wasn't sure I could, but here's, now,
way
admittedly
to
it's
do it.
AC only, but that's rated at 3,000 amps full scale.
You're gonna put it around here. My gosh.
You could calibrate your
Now,
shunt with this.
I could calibrate my shunt, although I don't
AC.
yet have a 50 ampere AC. But I'm working on that in my spare time. I got to go to Boston this week. I ain't going to measure anything of this sort this week, but another week we will do this.
Okay.
This is not hard to find another day, right? Keep it in, it works. We can measure.
Yeah,
Now, you got a bunch of things to set up to show us?
that's
what else
correct.
you got?
Yeah,
Let's
let's
see.
shall we
Alan,
go to the
show us
lab
what you
segment,
got.
or do we have anything else?
I don't know. Do you want to bring stuff up on the table and show us? or-
Well, let's show off one of the 428Bs
Oh,
and we'll compare it with
do you want me
something
to go
newer.
get that, or?
Yeah.
Oh, you want to bring one
Paul
over?
can
Sure.
swing back
Just
and
slide
get it.
this over
I don't want
gently.
to walk in front and get the cameraman mad at us.
Danger, Will Robinson. Be careful how you apply that to me, Paul.
If you put it in the web of your finger like a clothespin, will it hurt after an hour or two?
I don't want to find out.
So do you want to bring it back
Bring it
over
over.
here and put it on the table, Alan?
Yeah,
Sure.
I think the
This
focus
is
will
one
still
of
be good.
these.
Yeah,
Yeah,
this is
we
one
have
of these
several.
instruments on the bottom.
Ready, set. And I think it'll be a reasonably
It'll
good.
be out of the focus plane.
Nah, it's close enough.
We got crack
Okay.
crew here.
There we go.
Oh, that's a
That'll
good
work
picture.
better.
They know what to do.
Bob and
They're the experts.
Now, of course, HP in the
Yeah.
old days is Agilent today.
And
I think Carly did
HP
that
doesn't
backwards.
make these anymore, and Agilent doesn't make these anymore.
Ah, that's
but it's too
sad.
bad.
That's
Have you got this in the picture, please? Center on this. It's a good old analog instrument, and we will use this to calibrate some stuff one of these days.
yeah. It's got a real toggle switch in the back. Nice metal.
Yeah, actually, that's a degaussing section. Because it is good to a milliamp full scale on the most sensitive.
Oh, you're
setting.
kidding.
But
And
This thing is
it's
great.
easy to magnetize these probes just through the application and removal of power
that's
in
the
the
one.
circuit that you're using.
Wait a minute. This one doesn't open up, does it?
Yeah.
Oh, it opens.
Yeah.
Okay.
So you pull back
that up.
on the cowling, and the jaws
The jaws open.
open, and you clip it around the wire. You know, that's actually a subject we didn't really touch on.
What happens if you clip it around its own wire? Have you thought about that?
Explode.
Will this cause the end of the world as we know it?
Probably so.
Okay. Let's go look at the lab. This is a great old machine.
And how many of these do you have? They're stacked like
There's
cordwood.
25.
Well,
25.
25. Some of
Leave
them are
one or-
parts donors, so they'll never live again.
Yeah,
leave
they
leave
won't
one or
work.
two in here at the lab, and we want to evaluate it sometime.
Yeah,
Don't
is it
worry.
fairly standard stuff inside that you can buy the parts for? Or?
It's got a lot of custom transformers.
Yeah.
You know, so the
And if
R's and
that's
C's
on-
and the tubes are all widely available, but the custom transformers, once they die,
Yeah.
you
Goodbye.
may have a boat anchor
Parts,
on your hands.
Parts machine. Well, do you want to go to the lab now?
Let's go to the lab.
We got all kinds of good stuff stacked up here.
We-
We got all our good stuff in the bench. We got our magnifier, because all the parts are getting so small now, you need a magnifier.
Especially the
Yes, especially this delicate stuff that we
delicate
use.
stuff. Oh, man.
Because National's cool, they bought us all microscopes, so we got this beautiful Motec microscope. I love this thing. Works great. It's
You might turn the
inexpensive.
eyepiece around.
Well, we get 6 amps out of this,
It's got a camera on it. 6 amperes. Okay, that's
I
enough.
think.
Let's blow something
Let's
up.
see. Of course, I still believe that.
About 6.8 amps.
Well, that says 3.69, 3.18. And hey, guess what? This is getting warm.
Yeah.
So you're dead shorting a power supply.
Are you
Just for
tying
giggles.
two of them together?
Yeah, they're paralleled.
Oh, okay.
So you add those two together.
6 point.
Oh, you press those buttons in the middle. You know how to do that?
70?
Yeah, I did
Cool.
an advanced class.
6.87. 6.87 is reasonably close to 10 amps. It's to 7 amps.
Yeah.
So this is one way. I have some other cool stuff here I wanted to show off because we get the good stuff at National.
Good stuff.
All these people at these low budget companies
you
are
guys
crying
zoom
when
in.
they
That's
see
good
this stuff. This is a differential probe. It's not a current probe, it's a differential probe. And this is good if you have a circuit that's floating. You can have a little resistor in there and you can hook it across the resistor. And it doesn't matter if it's floating, it's got common mode voltage. Paul, you warned me about this though. You said you
Yes.
can get burned doing a resistor.
Using regular scope probes, or using the good old scope probes like this inside a switching power supply or a TV set or something like that, because there's so much magnetic flux flying around that the scope probe, we can probably show this when we get this fired up, will pick up signals better
It's-
than the signal it's actually trying to pick up.
It's
It'll-
difficult to reject those noise signals and difficult to see the signal you wanted to see.
Yeah.
Right.
But this could help.
Yes.
Now, there's a lot of differential probes that work at 20, 30 kilohertz. This is a 1 gigahertz differential probe, which is why we bought it. We like the good stuff here, and thank God our bosses are willing to buy it for us. There's also the newer versions of what Alan has here. This is the new Tektronix current probe. Here's a medium range one, same principle. And then Alan has a whole box of really good stuff. Here's a,
Yeah.
I don't know, does this predate the one underneath it, Paul?
No.
They're both
This is
contemporary?
actually this is actually the older one. This is the original. This is the fancy dancy new one with the
Digital display.
digital display. And
I complained, I said, where's the probe? And somebody said, it's in a little shelf in the box here. So what else we got to see here?
Okay, this is the 100 amp version of the black probe. The black
So-
probe's rated to.
plug that in.
So this would plug into the
Yeah,
same...
it's the same mating
either-
connector.
Same mating
Either one.
connector, which is a little different from the modern one.
By the way, there ought to be a warning label on these which says do not open the jaws on this in a circuit that is energized. You can damage the probe by doing
You
that.
can damage your
And I
butt.
own a lot of these things that I picked up used, and very few of them work because somebody damaged it. It says so in the user's manual, but there should be a warning label on the
So
top.
you're breaking the magnetic path.
breaking the
and you've got
magnetic
current
field,
flowing
and just
through it.
think what's happening to the magnetic
Rip it.
gap here when you've got a huge current flowing through the conductor.
I'm lost. It's flowing through the conductor, you break the magnetic path, and it's what's got a sense winding.
It all goes to L.
Yeah. It all goes to L. I think he's got it.
Oh, so if instead of a transformer now, it's just
Yeah,
straight
well, there's a
inductor,
lot of
and it
transformers in
kicks.
here.
Ah.
And you get these huge excitation voltages that break down the internal circuitry inside the
oh.
probe. It doesn't damage the preamp, but it damages
Right.
the probe.
Ah. And is it like JFETs or something that's available to fix, or have you figured out how to
I
save
haven't
them?
figured out how to save them yet.
Okay, well, we're going to have to
It's
call
all
in the
potted
cavalry.
inside these.
Oh, God, I hate potting.
It's difficult. Hey, we're in the show and tell racket. What do you got in your paper bag, man?
Well, you had some fairly hefty ammeter shunts. Here's some smaller ones.
oh yeah.
This one is a 5 amp shunt, I think. It's usually, yeah, this is a 5 amp shunt.
Can you focus in on that one because it's a fairly small wire. It's fairly
Yeah.
compact.
So it's low thermal coefficient type of wiring that's between the brass plates.
Probably manganese or similar. Okay.
Yeah.
Next
and,
show and tell.
These generally were made to be used with analog meter movements.
That's the whole point. Yeah.
So you get a 50 millivolt signal, it runs your 50 millivolt meter movement,
Yeah.
and life is good.
We'll be showing the 428B here. This is the larger version of the probe. It's still only rated at 10 amps full scale. Be very careful with that. Don't let the jaws smack together. It even has a dash pot in the handle to prevent that.
Oh, look at that. That's great. And that's,
That's a
you
monster.
chip the ferrite?
Yeah, you can chip the ferrite.
And
And
then
it's
you-
a very carefully sawn toroid of ferrite.
And they want to keep the area constant over the
Yeah.
gap.
Wow.
It amazes me you can have ferrite probes that measure DC.
Yeah.
And they do that just by integrating that signal through them, right?
And, it's funny you bring that up. There are many current probes that are made exclusively for AC. And you may find these laying around. The giveaway is that they're usually terminated in a BNC connector. So these do require a termination box of some sort. But, these are widely available in the surplus market. The smallest of which is the Tektronix CT1. Here's one in the original bag. It's never been
That's
used.
a good find.
And I paid $1 for that at a swap.
Oh, you're kidding. at the
I'll
a
bid
Foothill
two.
swap.
The Foothill
I'll
swap
bid
now.
$2.
The Foothill swap moved up to Moffett Field, so it's a mile. Even I
Yeah.
can get up at 6 in the morning for that.
And here's a larger current transformer.
You're
This is a wide
kidding.
bandwidth Pearson. These are quite valuable.
I see Alan at the swap. I know he gets there earlier than I do, and I see why. That's a great buy. So every kind of current. Here we went over to Alan's lab. This is what he's done. He's taken one of his power supply boards, one of our flyback. This is a straight flyback power supply. And he lifted the diode. I said, well, we'd like to show something. Maybe later on we'll get this hooked up. We'd like to show some of these current probes working. And you can see he just lifted the diode on the demo board here, soldered in a big loop of wire.
That's
and-
not necessarily a fair thing to add. You know that.
Well, it can cause you, puts a little
it
You
may-
inductance
got to
in.
realize, though, that often you're putting some inductance in series with inductance that's there already as part of the circuit. So in most cases, it doesn't hurt you adding the sensing loop.
It doesn't lie, huh? What does Spice say about this? We'll discuss this later.
I don't think
But
Alan's
it
a
may
big
work.
Spice devotee. Maybe he is. I don't know.
It has its place.
It has its place in the garbage? No, it's good
No.
stuff. Okay, well, we've learned a lot about current sources. Thank you, Alan, for coming over and
You're
bringing
welcome.
some of your precious test equipment. If you're in the Bay Area, look for Alan. He'll come over and help you with the circuits. Bob, anything else?
Wait a minute. He can only work on currents. He can't work on voltages. He's a bum.
No, he does both.
He
He's
does
good,
both.
he's good at both. Oh, I wanted to thank Hearst Business Publications, the electronic products people, and EEM. They do great stuff. They have it on a CD now. You can search it. I love that for not just semiconductor chips, but anything you want to search in the electronics world.
Current sources.
Current sources, really.
Maybe so. Anyhow, we hope you guys had a lot of fun with us today. We hope you learned something about current sources. I even learned something about current sources. So thank you very much for attending. Bye-bye.